Professor Maginn graduated at Iowa State University, where he received his bachelor's degree in chemical engineering. He then got his PhD degree, also in chemical engineering, from the University of California, Berkeley. He's currently the Dorney Family Professor of Energy Studies and the chair of the Department of Chemical and Biomolecular Engineering at the University of Notre Dame, Indiana, United States. Professor Maginn has a great interest in the understanding of the link between the physical properties of materials and their chemical constitution. He's a preeminent researcher in the field of molecular simulation, we all know that, whose focus remains on energy and environmental applications. Professor Maginn has also an interest in the development of new computational methodology for both MD and MT. In this case, we can highlight the open source code called Cassandra, which is a well-known Monte Carlo package. We all use it. Nowadays, Professor Maginn has more than 244 publications with more than 15,600 citations. But more important for us, Professor Maginn contributed a lot to the development of molecular simulations in Brazil. We can say that the field here completely changed after two of his fundamental courses. The first one was about molecular dynamics, and the second one was about Monte Carlo simulations. We actually have several Brazilian former students of Professor Maginn in this meeting today. So I will stop my screen share so Professor Maginn will be able to share his screen. And I would like to thank you in advance. And on behalf of the group, I would like to say that the stage is yours. We cannot hear you, Professor.
Okay, can you see my screen now?
Yeah. Yes.
That's okay.
Yes.
All right, great. Well, thank you for that very, very kind introduction. And I really appreciate the chance to do that. We went no seminars for months, and I've not traveled at all for several months now, and I'm missing the interaction with people. And so this is a really great chance to get to see some old friends, maybe meet some new friends. I see a lot of familiar faces and names in this list, so I really appreciate you all coming out to listen to this talk. So if I move my cursor, can you see that okay?
Yes, yes, we can.
Okay, so I'll use this in lieu of a laser pointer. What I wanted to talk about was a series of small stories about how we've used molecular modeling and simulations to look at the design of new materials with the focus on, really, I want to focus on two areas. One is the separations area, and the second is energy storage, in particular thinking about electrolytes for different energy storage mechanisms. Before I do that, I wanted to look back. Almost 10 years ago was the first time I visited Brazil. And Fred invited me, very gracious host, at this workshop, which was mentioned by Thiago. Great attendance, and this was the first one on statistical thermodynamics and molecular dynamics. You may have remembered Craig Tenney, who was one of the instructors. And I learned the term, what was the term for people from Rio who are more relaxed? Help me remind, I can't remember, what was this called? Carioca, right?
How to be a carioca.
How to be a carioca. So I was told I was not a very good carioca when I showed up, but at the end, after a week or so, I became a much better carioca. So that was a lot of fun. You can see some of the pictures here from the workshop on our boat trip. We were doing some Python coding even back 10 years ago. Here's Fred, Lucien, some other people. So that was a lot of fun, and I really enjoyed that visit. And then, as was mentioned, I came back again in 2012. So this is great friends, really good experience for me. I thought I would give you one slide on my university. So this is our faculty. We work in really 4 main areas of chemical engineering: soft matter, nanomaterials, energy and sustainability, excuse me, bioengineering and medical diagnostics. This is a really big area. Several of our faculty are working on COVID-19 detection and prevention methods. And I was pretty happy that the US government quickly instituted a grant program. And so about 5 of these faculty members now have fairly good sized research grants that are working on various aspects of COVID-19. And then I'm in what we would call the molecular simulation and data science cluster, but of course we all collaborate together and work together. My university is located here, this little red dot. So this is not too far. Chicago, Illinois is right here. So we're fairly close to Chicago. This is Canada. So we're kind of in the north. This is what our campus looks like right now. It's spring here, beautiful trees that are flowering. These people are not practicing social distancing. This was taken last year. So there aren't many people on campus now. It's kind of closed. But this is a little bit about our department. Okay. So I want to motivate the topic here by talking, first of all, about why separations are so important. And then I'll talk a little bit about energy storage. But especially for some of the students and postdocs, I think it's really important that we realize that the profession that we're in science, has a tremendous impact on the world. And a lot of us, we were talking before this got started, we get frustrated with our political leaders sometimes, who maybe don't appreciate some of the challenges we face in terms of energy and climate. But we can, in some sense, ignore the politics, and we can work on the science that's going to enable us to solve these problems. And ultimately, I think we're the ones who are going to solve these problems, not the politicians. And I'll just point out one of the areas of energy that's an energy intense user is chemical separations. There's this beautiful paper published a few years ago by David Scholl and Ryan Lively in Nature that talked about 7 chemical separations to change the world. And I apologize, my statistics here are going to be focused on the United States. I usually give a talk like this to a US audience. The numbers will be a little bit different for Brazil and for the rest of the world, but I think that the message is still the same. Separations account for a tremendous amount of the industrial energy use. So non-thermal processes could really help reduce energy use. So if you look in this pie chart here in the United States, industrial users of energy are about 1/3, and of that use, chemical separations are about 1/2 of that. So this is things like distillation, drying, tremendous amount of energy savings. If we could replace these with, say, membrane-based separations, maybe adsorption-based separations, we could have a tremendous impact on energy use and then CO2 emissions as well. So there's a really good reason for us to think about working in the areas of coming up with improved separation technologies. The second area is, I think we all realize the importance of energy storage. This plot in the upper left, you can see is from the IPCC. It shows the tremendous amount of increase, and this is gigatons of CO2 emitted per year versus time. And this is all being driven by fossil fuels, cement production, and flaring. In the US, you can see that greenhouse gas emissions kind of break down into electricity in the grid and transportation. These account for over 1/2 of the greenhouse gas emissions. So if you were able to reduce the CO2 emissions associated with the electric grid and with transportation, you could significantly impact the emissions. So how would you do that? Of course, you'd need to have large-scale energy storage to enable renewables like wind and solar to be used. Now, one of the things we were having our presidential campaigns, and one of the candidates who I respect a lot said, I'm just going to push to completely electrify our cars. We're going to have all electric cars. And my point is that's not enough, because on this plot, you can see grams of CO2 emitted for electric vehicles, depending on where the source of your electricity comes from. And here's the range of gasoline-powered cars. Now, in Brazil, you have a lot more biofuel. In the US, we have about 10% of our gasoline contains ethanol. But if you have an electric car that runs on electricity generated by coal-fired power plants, you're actually emitting more CO2 than if you just drove a gasoline-powered car. So what's the key? Well, the key is we need to derive our electricity from nuclear, wind, hydro, geothermal, things like that. And that means we need energy storage. So better batteries are going to enable electrification of transportation, and that's a significant amount of the CO2 emitted. The other thing I guess I'll just leave us with is that this is a tremendous market. The market potential of this is roughly 10 times the personal electronics market. So as a chemical engineer, we often worry about computer scientists and electrical engineers are taking over the world with all the electronics. This market here is way bigger than the personal electronics market. So what do we need? We need better energy density, so we have ranges, and we need cheaper batteries. So these, I would encourage people to think about. Working in these areas is really a good way to help the environment and try to change the balance of how things are going these days. Today in the US, we have about 23 gigawatts of energy storage capacity. 96% of that looks something like this. This is just pumped water. So what you do is you have a power plant here, you have a topography of land where you can have a high elevation. So when you have excess capacity at night, you pump the water up and then you let the water come back down. This is very cheap, it's efficient. Most of this was built a long time ago in the United States, but it relies upon having land like this. And if you look at where I live, the land is completely flat. You can't do this. So one idea is large-scale flow batteries that are coupled with, say, solar fields. And that would be another way that you could think about storing energy. The key limitation is this is too expensive. Right now, it's cheaper to just build new natural gas-fired plants rather than install solar and have energy storage. But if the energy storage piece could be cheaper, this would be competitive with natural gas plants. And the last motivational thing I wanted to just show here was that there is great capacity, at least in the United States, I think in Brazil as well, for wind and solar. Most of the renewable energy growth in the United States has been in wind. You can see it's really grown sharply. And the hope is that we could get 40% of our electricity in the next 10 years from totally renewable sources. And so that would be great. So we're going to have this energy storage capability to deal with that. Okay, sorry about that. So I want to talk about two topics that are related to these areas. The first one is involving gas separations. And here I'd like to show how simulations can be used to look at the development of, excuse me, of supported ionic liquid membranes that can be a low energy way of doing gas separations. So the first part of my talk will focus on that. And then the second part will talk about advanced simulations of electrolyte solvents for batteries. And so this is just a little cartoon of a lithium-ion battery. And here we're going to focus on the electrolyte that's really key for the solvation of these different ions. Can we move beyond the conventional lithium-ion battery to do better? So how we model these computationally, both ionic liquids and electrolytes, you'd like to start with the most fundamental modeling possible, and that would be solving the time-dependent Schrodinger equation. If you do that, you can get information on, say, small species. This is a picture of a ionic liquid ion pair. You can solve for the structure, the vibrational frequencies, energies. You can solve for charge distribution. So this shows you red is negative, blue is positive. You can understand the way the electron cloud distributes. But the problem with these quantum calculations is they're very expensive, and so you can really only look at a small number of ions or short timescales. What we'd like to be able to do is compute bulk properties. And so for that, we need a way of coarse graining the energy so that we don't have to solve this expensive equation every time, and that's a classical force field. And I want to mention here, please stop or raise your hand or do whatever if there's a question during the course of the presentation. So the kind of classical force field that we use in our simulations is a kind of a very simple, it's been around a long time. It treats things like bond stretching and bond angle bending in terms of a very simple harmonic type potential. You have rotational barriers for dihedrals that are sort of a cosine series. And then we treat what we call non-bonded or intermolecular interactions with a combination of some sort of repulsion dispersion interaction and then partial charges. And the key is that once you set these parameters, you've basically picked your Hamiltonian, and then all the properties of your system are dependent upon what that Hamiltonian is. You only need to do simulations to discover what those properties are. So the more faithful you can represent the real energy of the system with this approximate coarse grain potential, the more accurate your property predictions will be. So we try as much as possible to derive a lot of these from quantum calculations, in particular these what we call intramolecular terms, as well as the charges. And then to the extent we can even get these non-bonded repulsion dispersion terms from quantum calculations, we do that as well. So I won't say much more about that, but that's a big focus area of doing that right. And then we carry out simulations, either molecular dynamics, where you know the energy as a function of position. By taking the negative gradient of that, that gives you forces, and you can then solve a Newtonian trajectory. This is an ibuprofen molecule. It's actually surrounded by water. I'm just not showing you the water. You can also use Monte Carlo methods, and I'll talk about both of these methods, where instead of a deterministic trajectory, it's a stochastic trajectory, where you make random moves between old and new states and calculate the energy differences, and then accept or reject those moves with this rule that satisfies the underlying thermodynamic probability density distribution. So this method allows you to calculate the thermodynamics of your system. MD allows you to calculate both thermodynamics and transport properties of the system. So again, we develop methods that try to do this in a better way, smarter way. So those are the two kind of aspects of the tools that we use, and then the key is applying them to different types of systems. So the first system I'll talk about are ionic liquids. Most of you, I think, know about ionic liquids. There's a huge chemical diversity. You have these fairly complicated cations, some simple anions, some complicated anions. When you pair these up, if you do it right, they form a liquid that's liquid even below room temperature in many cases. And when I got started in this area maybe 20 years ago, these were sort of looked at as kind of curiosities that were interesting compounds, but nobody thought that they were really good for anything. Turns out that over 20 years and a lot of research, now there's a lot of examples of industrial applications of ionic liquids. There are two here I just wanted to cite that are very large scale, an alkylation process that's in Colorado in the United States by Honeywell, UOP, and Chevron. And then in Indonesia, a mercury removal from natural gas process that's Petronas they've developed. Some of you may know Mark Shiflett. He's writing a book that I think is out or soon to be out, where he describes various known commercial applications of ionic liquids. And I think he's got well over 100 of them that have been publicly announced, and he suspects that there are many more of those as well. So we even started a company that is working on commercialization of ionic liquids in a plating operation. So it's ionic liquid solutions. So these are no longer curiosities, they're real, they can be used. And so one of the things we wanted to do was to try to use simulations to understand how can I tune the properties of these ionic liquids to get the particular desired properties I need for a given application. And the one I want to focus on today is using an ionic liquid in what's called a supported ionic liquid membrane. So the idea is you could take a kind of a standard membrane, maybe PTFE porous membrane, and let's say you were interested in separating CO2 from nitrogen. You wanted to do flue gas capture or something like that. Well, we know that the permeability ratio of two species I and J is equal to their diffusivity ratio times their solubility ratio. So the faster a species can move through a membrane, the higher the permeability, and the more that dissolves in the membrane, the higher the permeability. So if you had a situation where nitrogen was impermeable and CO2 was very permeable, you'd have a really big solubility ratio. If the diffusivity ratio is roughly 1, that would dictate your permeability ratio. You could separate CO2 from nitrogen. So the idea here is take an ionic liquid, immerse the membrane in the ionic liquid, impregnate the pores with the ionic liquid. And if we could tune the ionic liquid to get very high solubility selectivity for CO2 over nitrogen, maybe we can make a good membrane. And the advantage of ionic liquids, of course, is that they're essentially completely non-volatile. So this becomes a stable supported liquid membrane. So if you wanted to do a calculation to predict this permeability ratio, what would you need to know? You'd need to know the binary solubilities. So you need to know how soluble is, say, CO2 and nitrogen in this system. And you also need to know the binary diffusivities, okay? Well, solubility is something we can calculate with Monte Carlo methods, and diffusivity we can calculate with molecular dynamics. So that's what we did. And then we just built a very simple model, take a graphite slit pore as a model of a membrane, change this pore size, and then put the ionic liquid inside and calculate these two different quantities and try to predict the permeability ratio, okay? So that's the simple concept of what we're trying to do. I'll quickly show you how we did that. We used this code Cassandra, developed in our group. I'll say a little bit more about that. We've released a new version of this. It's now on Conda, so you can just use a Conda forged compilation of Cassandra. You can get this from our GitHub page now. And there's a whole bunch of other tools that are now coming out. We're part of a NSF project to make running these calculations much easier. So Lucienne, I know Lucienne did a lot of calculations of adsorption in a zeolite with her student Sarah, who I think Sarah's here too. We've now been able to write a little Jupyter notebook, Lucienne, where we can basically run the whole methane adsorption isotherm from start to finish, setting up the calculation and getting the isotherms in about 15 minutes on a laptop. So these tools are really making it easy to set up and run these calculations. And I could talk more about that if people are interested in the end. So what do? We set up a two-box Gibbs ensemble calculation where we have an ionic liquid phase and a gas phase. And through Monte Carlo moves, we make sure that the temperatures, pressures, and chemical potentials are equal. For a given pressure in the gas phase and a given temperature, that would set the composition of the gas in the liquid phase, and that would set one point on an adsorption isotherm. So we do that for these different ionic liquid systems. Here's just an example. I'll try to show you pictures of some of the people who ran these calculations over the years, Eliseo and Ramesh. So this is the pressure of CO2 versus mole fraction. And in this particular ionic liquid, there's lots of experimental data. The simulations are in blue. And you can see we do pretty much almost quantitatively matching the CO2 solubility. And you can do that as a function of temperature. You can get enthalpies of absorption. So I won't go through many details, but we've done this for lots of different systems. And so for gas solubilities and ionic liquids, we're pretty good at being able to make those predictions. If you wanted to do this, the diffusivity, what you would do was do molecular dynamics. So here's a little picture, a little movie of an ionic liquid. The ionic liquid molecules are just shown as kind of wire frames. And here's a single CO2 molecule. And what you can see is it just bounces around, takes this sort of stochastic Brownian type motion. From that motion as a function of time, you can calculate a diffusivity. And again, we've benchmarked diffusivities versus things like NMR, and these are pretty accurate as well. So what my student Samir did was go ahead and do those kind of calculations for different types of supported ionic liquid systems and see what he got for permeability ratio. So this is the permeability ratio over here, PI over PJ. For here we're doing CO2 over methane in this particular ionic liquid. So let me walk you through what this graph shows. What he did first was he took just empty 2 nanometer slit pores of graphite. He calculated the diffusivity ratio, the ratio of CO2 to methane diffusion, and it's about 1. There was no real selectivity. The diffusivities are about the same. The solubility ratio in orange is about 2. So CO2 is about twice as soluble as methane at a given pressure. And so you take the product of those two. So this diffusivity ratio is actually a little bit less than 1. So this number comes down. You don't get much of a separation with an empty pore. And if the pore is even a little bit bigger, you still don't really get much of a separation. Then what he did is he took a bulk ionic liquid, not confined in a slit pore. you see the diffusivity ratio is still about 1, but now the solubility ratio goes way up. So CO2 is much more soluble in an ionic liquid than methane is, 6 times as soluble. And so when you take the product of those, you find a permeability ratio now of about 6. He then put the ionic liquid in a 2 nanometer pore and a 5 nanometer pore, and he saw an even higher increase in the total permeability ratio, driven mostly by an increase in the solubility ratio under confinement. So CO2 is even a little bit more soluble than methane when you have a confined ionic liquid. So we're able to predict selectivity ratios of around 10 for this type of a system. He did this also for CO2 hydrogen. This shows very different type of behavior. The diffusivity greatly favors the small hydrogen. So now the hydrogen is 10 times as fast through the pore. So that means that for these empty pores, you actually don't have much of a selectivity at all. You see a little bit of a selectivity, solubility in the pores, but you really don't see any separation in the empty pores. You see huge differences in solubilities of CO2 over hydrogen. CO2 is much more soluble in the ionic liquid than hydrogen is, but because the diffusivity of hydrogen is 10 times faster, when you take the product, you get back down to about permeability ratio of 10, okay? And what's interesting is if you compare that to experimental data on the same system, CO2, hydrogen, this is actually work that we did many years ago with experimental collaborators at the National Energy Technology Lab. So they fabricated these supported ionic liquid membranes, and these open symbols, which I'm calling physical solubility, that's the solubility mechanism that's driving the separation of CO2 hydrogen in this particular ionic liquid. What you can see is that at around, we're here at 50 degrees C, this is around 25 degrees C, you see selectivities of around 10. So this is consistent with what we're able to calculate with our simulations. I'm sorry, the physical solubility are the filled squares, and it plateaus at around 10. These open symbols are for a reactive ionic liquid, which I'll say more about in a second, and it's possible at certain temperatures to get even higher than 10 selectivity for this particular system. So that's interesting, and I'll come back to that in a second. But we were pretty excited that we're able to match this more or less quantitatively. Now, what about this reactivity? Well, it turns out that the physical solubility of CO2 is actually quite low. Normal solvents that are used to do CO2 capture have an amine reactive group, and you can get over 0.5 moles of CO2 to dissolve for every mole of solvent when you have a chemical reaction taking place. But in these ionic liquids I've been talking about before, it's just physical dissolution. So even though it looks like a pretty high solubility, it's actually not that high. It's you know, just a couple % on a mole per mole basis. So what we realized is if we really want to improve this solubility selectivity, we should think about adding chemical reactivity. So one way you can do that, which we've shown years ago, was by tailoring the anion so that it has an amine, a reactive amine group. So here's just a very simple glycinate anion. So we just use glycine, an amino acid. And it turns out that that'll react in a 1-to-1 ratio with CO2 to form this species. So this looks pretty good. I had a visiting student from the Matsuyama group in Japan who came, and he was doing experiments, but he wanted to learn to do simulations. So he spent some time in my lab, and he had done some experiments with this glycinate anion and then a kind of a big bulky phosphonium cation. And he'd measured the amount of CO2 that absorbed per mole of this particular ionic liquid as a function of temperature. And he was seeing even, you know, greater than 50%. It was approaching 1-to-1, which we had predicted it was going to be 1-to-1. And so if you look at this relationship between the permeability ratio is going to be the diffusivity ratio times the solubility ratio, this suggests really high CO2 solubility. So you've got a really good, strong driving force to get high selectivities here. Unfortunately, what he also learned was that the viscosity of these systems is pretty high to begin with. And as soon as you start reacting it with CO2, the viscosity goes up by a few orders of magnitude. So you're talking about 100,000 centipoise viscosities at room temperature. So this doesn't flow at all. And since the viscosity is high, that tells you that the diffusion of the gases through this very viscous liquid is going to be very small. And so that's going to hurt you, right? So that's not good. So we had done work a long time ago, a postdoc, Keith Gutowski, in my group, and he showed that the reason for this high viscosity increase is that this carbamic acid group is capable of forming hydrogen bonds. So you could think about making reactive anions that don't form hydrogen bonds, something like this, or an aproto reactive ionic liquid. So the prediction here was that these won't show much of a viscosity increase. So the question is that true? And we published this a few years ago. Sure enough, when Aki ran the viscosity measurements for this new ionic liquid, which is in red, you see just a very modest increase in the viscosity compared to the tremendous viscosity increase with the old glycinate ionic liquid. So what that tells you is that the gas permeability, now I'm not looking at the permeability ratio, just the total permeability, how fast the gas goes through the liquid. What you predict here for nitrogen is shown in the black. It's lower than CO2 because the CO2 has a higher solubility. The blue curve or blue line is for the old ionic liquid with the glycinate anion, and the red one is for this new anion that doesn't show the increase in viscosity. And so at low temperatures, you can get almost a factor of 10 or even more permeability of CO2 through the membrane. So this just means you need 10 times less surface area to get the same amount of gas to transverse through your membrane. So this was great news, and this was experimentally determined, and so that's really great. And I'll come back to those old experiments from 2008 that were run. And remember, I had shown you data for a physically dissolving ionic liquid and for a reactive ionic liquid. And although the permeability ratio in the reactive ionic liquid was a little bit higher than for the physical solubility, the actual permeability, how much gas goes through the membrane, drops with this old-fashioned reactive ionic liquid. And it had a reactive group actually on the cation, not on the anion, but these suffer the same problems that the other ionic liquids I talked about. And so that's consistent. If you look at these sort of permeabilities at room temperature of around 10, that's pretty consistent with what Aki was seeing. But our predictions are that you should see room temperature permeabilities way up here, maybe around 1,000 for these ionic liquids because the viscosity doesn't increase. So we should see more or less almost a flat curve here. So let me go back one slide. So that's the end of this story. And I've had several people ask me, if this looks really good, why did you guys extend this? Did you do more work on this? And the answer is we did some more theoretical predictions, but Aki got a job and left. And the Matsuyama group did not, as far as I know, follow up on this. But I think there might be some of you in the audience who might be interested in working on this, and maybe some of you already have. And I'd be curious to see if these additional predictions we made, we can tune the viscosity of these things to get them lower and even predict higher permeabilities yet. And I'm curious, I'd like to see some experimentalists follow up on this. Every time I give a seminar, I kind of ask people, could you maybe look into this a little bit more? So maybe this is an area that someone would like to look at. So that was the story of how we calculated gas permeabilities and permeability ratios. I could stop for a minute, and if people had a question or a comment or something before I move on to the next one, let me do that. I think there's a chat feature, or raise your hand or just start talking.
Open for questions, please.
And I could make a couple comments and then ask a question.
Sure.
This is Richard Elliott. So I just thought I'd mention that Fred had mentioned earlier that I gave actually it's 2 lectures. One was more of a introduction to phase behavior for the new graduate students. Mm-hmm. And then in that lecture, I sort of motivated, the interest in studying phase behavior like vapor-liquid equilibria through distillation. And so in there, I mentioned that it was about 70% of the capital cost goes into distillation usually, but I didn't mention the operating cost in terms of energy. So that was pretty interesting. One thing that related to that might be something the audience could help me out with, because most of my experience with this pertains to teaching process design to senior undergraduates for a few years, and so whenever I did a design, I just kind of looked at these things. One of the times I found a sample problem where they were doing separation of azeotropic ethanol using an azeotropic distillation with either pentane or hexane as the entrainer. And so I did the economics on that, or I just looked at the energy cost of running the azeotropic separation after you already were pretty close to the azeotropic concentration. What I found there was that you used almost as much energy to break the azeotrope as the energy value of the ethanol that was resulting at the end. So you had mentioned something about bioethanol maybe being able to overcome our limitations. According to those calculations, bioethanol is not really going to do that. I'm sure they have a better way of breaking the azeotrope than what I did, just kind of tinkering around. But I don't know if it can really be that much better. I'd be interested if somebody in the audience can give us a better idea of that. Then the other, I
know one thing about that. I can just, we have a large ethanol plant here in town. I've given tours. They use adsorption. They use zeolites to break the azeotrope. So they do an adsorption-based separation. And so that's an example, I think, of where it is pretty clear that if you can do adsorption or membranes, you could think about a pervaporation membrane. You're going to definitely save energy versus distillation. There's a whole nother question about if bioethanol is really helping you all that much, and that's a whole nother topic that I don't really want to go into right now, but that's a really good point. It's a really good point.
Then this is more of a technical question about Cassandra. One of the things that we've been using a lot lately to help us develop force fields is called MBAR, Modified Bennett Acceptance Ratio. We looked at Cassandra for putting that in, but it wasn't as easy to do that as it was to put it into GoMC, the Jeff Potthoff version of Monte Carlo. And so I was wondering if you guys have maybe looked at it, and being much more expert at Cassandra, it would be easy for you guys to put that in there.
Yeah, it's on our to-do list, actually. So we have an NSF project that's developing out, and you're exactly right. We want to do MBAR, and actually Jeff's involved in the same project with us, as is Ilya Seatman. So we're kind of collaborating to put all these things together into kind of a functioning tool. So look for that. That's coming out. Stay tuned. Yeah.
So is that a 6-month or 6-year kind of when it's going to come out?
6 months.
Okay. Okay. Thanks.
Okay. Let me keep.
We are organizing a Cassandra workshop with Edward Maginn. So soon we are going to launch an announcement about Cassandra workshop in Brazil. Well, in Brazil, it's not necessarily being in Brazil because maybe it's going to be online. So
probably be online, I think, for a while. But yeah, I think this maybe early summer or June for us might be a good time to think about that, Fred, depending on how it works for your schedule. But I'd love to show people some of these new features. It's really exciting what we've been able to do in a pretty short period of time. Let me keep going here. One of the things we asked about was everything I showed you with these reactive ionic liquids. We didn't actually calculate the isotherms. We just calculated the energy of the reaction using quantum methods and try to relate that to the capacity of the reactive ionic liquid. But what you can see, this is experimental data, the same cation, but a bunch of different anions, and you see very different isotherms. Some are weakly binding, some are very strong, some are in the middle. And depending on your process, you might want to be in the middle, you might want to be here, just depends. And it's really hard to predict what these binding isotherms look like. So we asked the question, could we just directly simulate a reactive isotherm. So we approached this in two ways. The first was kind of how a thermodynamicist would do this. We constructed a thermodynamic cycle. So what you'd like to do is you'd like to know the free energy of the reaction of a liquid ionic liquid and CO2 dissolved in it, and then you form a mixture. So here's the reaction. Again, we're taking a cation, we're taking this anion, and then we're sticking a CO2 on the anion. So this is the chemical reaction that takes place. And it's reversible, okay? Now the problem is, again, with quantum methods, we can't do this calculation. But we can do it in the gas phase. So you could take, say, an ionic liquid pair, CO2, and do this reaction. And there we can get a pretty good estimate of this free energy for reaction 3. So we constructed a thermodynamic cycle where we take and vaporize the liquid, and we use a... I'm sorry, is that a question? Okay, well, we vaporize the ionic liquid and calculate the free energy of this with a classical force field. We react it with the quantum methods. We mix the ionic liquid and the reacted CO2 with, again, classical methods, and then we bring it back to this ionic liquid mixture. So we can calculate all of these legs, the free energies. And I won't go into the details, it's all described in this paper here, but basically you can write the free energy of this reaction in terms of the extent of the reaction and the pressure of the CO2 that's above it. And then we minimize that free energy and we solve for the extent of the reaction as a function of T and P, and that gives you points on an isotherm. And so Quentin Sheridan did this as part of his PhD, and here's the results that we got. This is for that previous ionic liquid I showed you. Experimental data are these open circles, and we used 4 different levels of theory basically to do the calculations. And you can see, depending on your level of theory, the isotherms, they don't change in shape, but they change in value quite a bit. So I don't have time for the details of this. If people are interested, I can talk more about it. Basically, this is this bar method that Richard was talking about. We used a Bennett's acceptance ratio method to help us with the free energies. So the most accurate calculation is this sort of orange or yellowish line, and that actually does a pretty good job of matching most of the experimental data. We tend to over-predict the experiments. They never get up to 1, and we think that there's some impurities in the samples that maybe causes them never to get to 1. And then we can do temperature-dependent values as well. So this is pretty remarkable for this sort of pretty simplified thermodynamic cycle that we can get good estimates of these. A postdoc in my group, Ryan Mullen, said, I want to calculate this directly with a Monte Carlo method. So he said, why can't I just take CO2 in the gas phase, translate it back and forth with the liquid phase, and then allow reactions to take place with the Monte Carlo method? And there's something called reactive Monte Carlo, or RxMC. And if you could do that, you could actually just directly do this without having to construct this thermodynamic cycle. So Ryan worked all the details of this out, and there's several papers that tell you about how this all works. Basically, the assumption is that we can break our Hamiltonian into a classical piece that accounts for solvation and a quantum mechanical piece that accounts for bond forming and breaking. That quantum mechanical piece you can write as an individual molecule partition functions that you can calculate in the gas phase. So you can run a gas phase simulation of the reacted and unreacted species and calculate what this is. And then I have to evaluate a configurational integral over a classical force field to account for the solvation environment. And you can work out what the Monte Carlo acceptance rule looks like. It's very kind of messy, but there's a constant term out here that just depends on this quantum thing. And then a classical Boltzmann weight of the energies. And if there's no classical energies, if there's no solvent, it's ideal gas. And so this is really the ideal gas free energy of the reaction, if you will. So you can either look that up for systems that are known, or you have to calculate them quantum mechanically. So you have to input the reaction. The code doesn't figure out what the reactions are. You have to tell it what the reactions are. And you have to put in these ideal gas free energies, and you have to know the potential. So Ryan did this for CO2 in this particular ionic liquid. I'll just show you a movie of this. Imagine there's a big box of gas phase CO2 over here, which we're not showing. Here's the box of the ionic liquid. The cations are in blue. The unreacted anions are in red. CO2 will show up as black molecules when it gets swapped into this box. And then we let a reaction take place with the stochastic rule. And when those anions react with CO2, we'll turn them green, okay? So I'll hide the cations here so they don't participate. And you can see that every once in a while, a CO2 will transfer in, sometimes it transfers out, and then sometimes it reacts and forms a reactant anion, okay? So these things are just kind of wiggling around. This is in a Monte Carlo simulation. This is a short, very short piece of a really long calculation. We had to work for about a year to put in a lot of biasing methods to get this to be efficient enough that you could calculate it. And that's a big part of what Ryan solved. We did that, and then we check for equilibration. We start with either no CO2, 50-50, or almost all CO2, and they all converge to the same value after a long time. And then these are, again, predicted isotherms from these methods. Now what I'm showing you are the simulations have these open symbols with the dashed lines kind of going through them to guide your eye. And we've got now two different sets up here at, this is at 300 Kelvin of experimental data depending on two different cations but the same anion. And so you can see that makes a little bit of a difference. And the simulations kind of go through the middle of both of those points. For this particular case at 333, the blue, the simulations are nearly quantitative with the experiments. And then we made some predictions here at higher temperatures for which we didn't have experimental data. We just made some extrapolations. And here we're predicting a little bit lower solubility than the experiments. You can just kind of get a sense about what the population looks like at low temperature and at high temperature. You have a lot more reacted species at low temperature than at high temperature. So the way you would run this would be do the absorption at low temperature and then regenerate your solvent by heating it up and driving the reaction to the other way. You can calculate the Henry's constant and equilibrium constants from this. Again, I won't spend a lot of time other than to show you that basically the delta G of the reaction experimentally you can back out from the experiments. It varies as a function of temperature from about -6 to about 1.6 kilojoules per mole. And the simulations are predicting things that are pretty close to that with, at higher temperatures, a little bit of an offset. For those of you who know about quantum calculations and force fields, getting accuracy to within a couple kilojoules per mole is really, really hard. And so the level of agreement here is within a few kilojoules per mole, which is basically what we would call chemical accuracy. So this method has been implemented in a development branch of Cassandra as well. And we've applied it to some other reactive Monte Carlo things. So we hope to make that be available in the public release. So that's the first part. I spent most of my time, I have a little bit quicker now. I'll go through some energy storage. I want to be conscious of our time. We're already kind of running a little long, but I'll quickly tell you about just a few snippets of things we've been doing modeling electrolytes for energy storage. Nathalia joined our group for a while and worked with Yushan and Yang on a project that was sponsored by Toyota on looking at different types of organic solvents for lithium TFSI salts. So dissolving this particular salt in a lot of different organic solvents. And they wanted to know properties like the electrochemical window, how stable are these under a potential, conductivities, viscosities, diffusivities, dielectric constants and solubilities, and enthalpies of vaporization of the solvent. Sorry. So one of the things they did is they said, well, we'll give you data for 19 different electrolyte solvents that we've been working on. And could you use this information to develop a kind of a machine learning model to tell us how we could predict properties of other solvents? And so they did that, and here's the results of this. Basically, we used a lot of different descriptors in a genetic algorithm to select the best molecular descriptors. We chose 4 of them. Here they are. And the bottom line here is you can look at the model predictions versus experiments. Following on the blue line is perfect agreement. So this is the electrochemical window in volts. So it ranges from 3 to 6 volts. Here's the conductivities. Here's the oxidation potential and the reduction potential. And So this model, we trained it on the experimental data, and it does a pretty good job of getting that result right. So then Toyota said, well, this is great. Can you give us this model? And we did, and we didn't hear from them after that. So we presume that they're pretty happy with our model and using these kind of methods. For a little bit more physics-based approach, we wanted to go to atomistic simulations. And many of you I know on the call, I saw a lot of your names are very familiar with this new class of solvents that have been given the name. Sometimes people don't like this name, but often they're called deep eutectic solvents. All that means is you can take two pure species with their melting points and some mixture composition. The melting point's lower, that forms a eutectic. We know all about that from thermo, but these compounds have really deep eutectic points, so the melting point's quite low. So for example, if you took choline chloride that melts at 300 degrees, ethylene glycol, which is a liquid at room temperature, -13, but if you form this eutectic 2-to-1 mixture, which people call ethylene, the melting point's -66 degrees. So this is kind of interesting. And people have thought about these as being replacements for ionic liquids. So they have a lot of the same properties of ionic liquids in that they have very low vapor pressure. They're cheaper than ionic liquids, generally speaking. They have moderate electrochemical stability. So we're on a project looking at, can those be used for electrolytes? Like the ionic liquid literature, there's been a huge increase in the number of publications over a very short period of time. But what you'll see is there's a lot of discrepancy in the literature. You can see this is published viscosities for nominally the same compound, ethylene, and you can see a lot of variability between different experimental groups. And we think that this has to do with purities, water contamination. The ionic liquid literature had some of the same properties of this. So as a modeler, we'd like to know what the best properties are, or what the actual viscosity is, and can we model these properties? So Derek Poe has been doing some of this work. Here I'm just showing you that he's been able to model the density, viscosity, and the self-diffusivity of ethylene, comparing this with experiments. The agreement is not perfect. We're working with Burju Gurkhan, and she's doing experimental work. Here's her viscosity values. Here's a literature values. Good temperature dependence, but we're off slightly. We tend to predict in this particular case, higher viscosities than what's observed experimentally, and lower diffusivities. We've been working with people who do neutron scattering at Oak Ridge National Lab. Here's a comparison of experimental and calculated neutron scattering structure factor. The nice thing about the simulations is we can decompose this overall SFQ into individual contributions and say something about the organization of the liquid and what's responsible for these different peaks that we observe. We also working with Mark Tuckerman at NYU, and he's running AIMD simulations. And what you can see is there's some slight differences between the neutron scattering and our calculations, but the AIMD and our classical models give almost identical neutron scattering patterns. So we argued for a while, and we learned that there was an incomplete deuteration of some of the ethylene glycol and some of the choline chloride. And through changing the virtual deuteration in our simulations and then looking at the experimental evidence, we learned that this disagreement is actually due to incomplete deuteration. So here was an example of simulations really trying to help explain some of the differences that we see maybe experimentally. We can also decompose this and say something about the solvation structure of these things. A lot of times people think that this is the ethylene glycol molecule, that it would solvate a chloride like that. It does. That's the first peak in a radial distribution function, but we also see solvation structures that look like that, and that's the second peak. So again, the power of the simulations is we can understand the different solvation environments that these things have. And I know I'm really running out of time here, so we can get three-dimensional pictures that are very complicated. All point is I'd like to say is that this is a really complex solvation structure. It's dynamic. We can learn something about the exchange dynamics. We can do dielectric spectroscopy. We don't. Other groups do dielectric spectroscopy and relate that to some of the time constants that we get for these exchanges. And this is very much a work in progress, but this is some of the work that we're doing now. We're looking at dissolving, say, divalent cations in the solvent. So if you dissolve zinc chloride, can we calculate the properties and the solvation structure of this? And the answer is, yeah, we do a pretty good job. Again, here's scattering functions, density comparisons with experiment, viscosity comparisons. And then other deep eutectic solvents. Here's the same thing for this thing called glycerine, which is glycerol and choline chloride. So same kind of thing, diffusion, viscosity, density. So we're interested in comparing that with experiment. And then I just really quickly wanted to just touch on this. We're part of this Joint Center for Energy Storage Research at Argonne National Lab. It's a really large group that's been focused on things like multivalent cations, redoximer solvation, and the most recent thing that we've been focused on are these water and salt electrolytes, where you can take, now as a solvent, instead of an organic, we can take water. And if it's very highly concentrated salt in water, it turns out that the electrochemical windows can be quite large, much larger than the electrochemical window of pure water. So people have been asking, well, why is that and what's the structure of these things? So we've been able to match densities as a function of concentration for these systems. We've been able to calculate the dynamics. So the viscosity we match pretty well. Again, diffusion coefficients pretty well. And then again, we can answer questions about the structure. So what we find is when the molality is low, basically all of the lithium ions are coordinated by water. And then as you add, or you reduce the amount of water, basically increase the concentration, you start to see that the anion, TFSI, starts to solvate the lithium more, and it drives the water off. And we can calculate the fraction of TFSIs that are monodentate and bidentate and try to understand the picture of what's going on here. Finally, and then, again, add multivalence. We can add zinc into the system. Here's examples of, this is X-ray scattering now that was done at the Stanford Linear Accelerator. The MD simulations are the purple lines. The experiments are these points. And we're matching basically as a function of composition the structure pretty well. So this is very recent work. I would say we're just getting some of these papers published now, but I'm really excited. We have a really nice collaboration with a large number of experimental groups. So I wanted to leave you with this message. Basically, I gave you kind of two examples of using simulations for what I consider very important problems in the energy and environmental areas, namely reducing the energy cost of separations, and number two, developing improved electrolytes for energy storage. And you can use combinations of molecular dynamics and Monte Carlo calculations along with these new advanced reactive Monte Carlo simulations to, in this case, look at supported ionic liquid membrane design. And then we can also use things like machine learning, QSPR, and these simulation methods to get the structure and the dynamics and other physical properties of these electrolytes. And so here we're interested in deep eutectic solvents as well as concentrated electrolytes. That's been our kind of focus over the last 6 to 8 months or so. So with that, I want to show you some of the collaborators listed here that have worked with us. These are all experimentalists except for Kristen Persons, a quantum chemist at Berkeley who we work with. Students and postdocs who took part in this. I tried to show you pictures of them. And then our funding sources, people who helped pay for this. And if there is still time, Fred, for questions or comments or anything like that, I would be more than happy to entertain them. So with that, I'll stop. Thank you.
Thank you, Ed, for this very nice talk. We have, of course, time for questions because I think it's part of the seminar, some questions. So it's open. Don't be shy. Ed, let me ask you something. You have shown us separation between CO2 and other compounds like methane. But I wonder if you can use ion collect for separate methane by nitrogen. That's very much more similar in interaction and so on.
Yeah, that's a really great question, Fred. my short answer is I don't have a good idea for how to do that. There might be other people on the call who do, but in these physically dissolving ionic liquids, the diffusivity ratio is going to be basically 1. And as you mentioned, the solubility differences between methane and nitrogen for kind of the conventional ionic liquids we know about is going to still be about 1. So the hope you would have would be if you could figure out how to somehow engage the quadrupole moment of nitrogen and tailor your ionic liquids so that you could improve the solubility selectivity of that over methane. That would be the idea that you might have of how to do that. I don't have a good idea for how to do that right now, though. And maybe other people do have some ideas. But certainly you could think about using some of these computational methods to start screening ionic liquids and look at that.
Thanks. People, we are open for questions. We have a question for you that when are you going to launch the new Cassandra? Because in the website you cannot download yet.
Yeah. So let me, I just stopped sharing, right? Let me show you.
Because in this community, we have some people that are using Cassandra already, so, but they're not the new version.
Yeah, yeah. Okay, so let me show you. Let's see, you can't see the screen yet. Hold on. So if you go to our GitHub site, which I think I should be showing right now. So the old Cassandra website just has a static tar file of the kind of old release. It's actually version 1.2. On our GitHub site now, we have 12 different contributors who you can now clone and download the latest version of Cassandra. Here's all the information on this. We have a different documentation now, and you can become a developer of this if you'd like. So if you're interested in getting kind of the latest version of Cassandra or adding to the code, you would do it through our GitHub site here. And so I can help answer questions about that if you want. There's another piece of this that's called Mostef Cassandra. So this is a Python wrapper that goes around Cassandra. And what this does is basically, you can read about how this works, but essentially what this will do is you write a series of a Python script basically, and we use these other tools that are in this so-called Mostef development package. So mbuild allows you to build molecules. So can you guys all see this? I don't know if you read Python, but here if you wanted to just build a methane molecule, you would simply just give it the SMILES string for methane, and that's it. If you wanted to assign the OPLS force field for methane, you use another tool called Foyer, and you've now just assigned the force field. You don't have to write any, you don't have to code anything in. If you had a more complicated molecule, you would just use 2 lines of code like this. You apply the force field, you build a box in Cassandra. You say, make 100 methane molecules. Let's do NVT simulations. It creates a moves object, and then you run the Monte Carlo calculation for how long. So this is the entire way that you would set up and run a whole calculation. And what this does is it really frees the user up to not have to be manually typing in force field parameters, loading in PDB files and things like that. And you can see that this is very reproducible. So when you publish a paper, you can publish this script, and anyone in the world can then reproduce your results because they know exactly what you did here. So that's another feature that we're releasing in addition to improvements in the actual Cassandra code. And that's all available here at this Mostef Cassandra piece of our GitHub package. So I would be happy if people wanted to contact me later this is what I thought I would give a little seminar on, was how you use these tools and things like that, because it's quite a bit easier than what we were doing even a year ago, I would say.
Thanks. More questions?
I could ask a question about the MOSDEF interface. This is Richard Elliott.
Yeah.
So I tinkered with MOSDEF quite a bit a couple years ago. At that time, you know, I'm a little more interested in united atom models, like trap model, or extending that sort of the way Potthoff has. And the interfaces for those models, as opposed to OPLSAA, were they were very intermittent in their workability. Has that changed at all?
That has changed, yeah. So we can do now, united atom models are in there, and basically what you have to do, I don't get into too many of the details here, but there's behind this Fourier command here is this force field, and that's an XML file. So we've built now XMLs for trap UA, for OPLS, for GAF actually. We're building them for me potentials. So you can make any force field you want. You just have to create your own XML file and then call this command, and it will load the force field. So you can make your own custom force fields if you want. You just have to put in a little bit of effort to build the XML force field file for it. And then that would become part of the MOSDEF package. So yeah, that's the idea. So there's a whole new interface. MOSDEF has changed quite a bit over the last year or so, and it's still in active development.
So trap UA is complete now in MOSDEF?
Yeah, yeah. Ilya's group put that in.
Okay, thank you.